You said when we rotate the qubit on the black sphere, it may not go like, let's say, perfect 100 degrees. So it's not the perfect gate. So there is little error. But when we look at the physical system like this, the spin either this way or that way is the qubit. So when we change the spin, it should be either there or there. So there's no in between.
No, there is in between. So this has been unmuted? Is it all right now?
It's all right.
Okay. See, that's not true. So it's just parallel and anti-parallel. This is a classical picture. It could be in any direction.
Yeah.
But the energy will be different. So it could be a superposition. So when you look at Rabi dropping, the spin is actually a superposition of cat 0 and cat 1. So you can have superposition between these states. Right?
Yeah, but like I couldn't make the connection between the error correction part, like because in the error correction we assume that when we apply the gate, it may not be perfectly. I mean, there can be some error, but when we look at the physical systems, when we change the spin, it change. I mean, it is either changed or not changed. I mean, it's either in spin up or spin down. Is there error here? I mean, when like atomic energy levels, it's either in the up or down or superposition. But is there any error like with what we saw in the error correction part?
So there could be errors here in the implementation of quantum processes. There could also be errors in spin processes. By the way, in the quantum error correction scheme, the error correction is itself erroneous. So that is why there is a threshold of you add more redundancy in the ancillary qubits, kind of mitigate that erroneous error correction. The error correction can also be erroneous. So you add more redundancy in the auxiliary qubits or use more complicated schemes. So doing error-free error correction is also a research area in its own right. In this case, you also have errors. You also have errors. But the spin can be in an arbitrary direction. Quantum mechanically, the spin is, if it's in this state, it's in a superposition. You can't say whether it's aligned or anti-aligned with the. Only when you make a measurement can you say whether it's aligned or anti-aligned. Because when you apply a magnetic field, you are breaking the symmetry of space. You are applying an axis. And when you define an axis, can you say it's aligned or anti-aligned? If you have a spin in zero magnetic field, right? Then there's still a spin, but there is complete degeneracy in its energy. But there is still spin, you apply a magnetic field and the degeneracy is immediately lifted. Right. So I was talking about the interaction between two spins. So this interaction could be of this kind, right? So if you remember from your condensed matter physics, two spins can interact. This is called the exchange interaction. This is the Heisenberg interaction. The Eisen interaction is when you have an interaction of this thing S A Z S P Z. Okay, when you have the two components Z, X, or Y, and then you take the product of those two components. This is Eisen. On the top, you have Heisenberg interaction. Okay. So both of these interactions can exist. So there's interaction between qubits in the spin degree of freedom. The spin itself sees a magnetic field, so you can implement one qubit and two qubit gates in the spin picture, in the spin manifold. For example, let me also talk a little bit about, to give you an example. Suppose I have a spin, right? It's placed inside a magnetic field pointing along the z direction. This magnetic field lifts the degeneracy and changes the energy of the spin, therefore there has to be Hamiltonian associated with it. That Hamiltonian H is given by minus H bar mu some omega, some frequency, this is some frequency. This frequency is, I think, minus gamma times V, the bright field. Okay, and an operator S. Since the field is along the z-axis, an operator is also, the spin operator is also on the z-axis. So this is the Hamiltonian for spin inside a magnetic field. Okay, omega is called the Lamarck frequency. Higher the magnetic field, higher will be this frequency. So I forget the physics, I just simply write down through dimensional analysis that K is bar omega some energy term. S is an angular momentum operator. So this is the Hamiltonian of a spin placed inside a magnetic field. Now if you already know that if I have some quantum state at some time t equals 0, and if it's inside a field with some Hamiltonian, this quantum state is going to evolve, right, in this fashion. This is the Schrodinger equation, the solution to the Schrodinger equation. So at some later time, this is what the field is going to be. The quantum state is going to be. Okay. Now, if you kind of imagine, if your initial quantum state, say at time 0 is in a superposition, and this is your Hamiltonian, and you already know that your Hamiltonian in the Hamiltonian spin angular momentum operator is simply the Z Pauli operator divided by 2. Okay. So now the situation that is in front of you is that you have this state, and this is evolving in time study exponent minus I omega t z. Okay, so this is your state at some later time. Now you already know theorem. You already know that the square of z is kind of identity. So this thing is cosine of omega t over 2 identity minus iota sine of omega t over 2 z operator acting on x0 plus 1. Okay, so this is a state at some later time, which turns out to be cosine omega t over 2. Let's just call the state x plus. Okay. Minus iota sine omega t over 2 at minus. We get minus is this state is minus sign diagonal direction. So after some time, when you place the spin inside the magnetic field, it evolves with time into this form. Okay. Now this is actually z qubit, z rotation on a single qubit. If I were to plot this on a dot sphere, I can just go back to L0 plus 1 and 2 minus iota sine omega t over 2 minus 1. This just turns out to be E minus I omega t over 2 at 0 and E at 1 single right? This is what it turns out to be. So I just take a global phase factor outside, and let look at 0 plus E element of G. Okay. So on a block sphere, this is an evolving state. So this is my block sphere. Omega G, sorry. Thank you. So now this is my evolving state. So start off here, get 0 plus 1. I have placed the spin inside the magnetic field. So it's really a z rotation, a rotation of the z axis due to this Hamiltonian. And this spin starts to recess in the equatorial plane with the frequency minor. So it starts to move around the equatorial. So this is a z gate on a single qubit. I can also apply an x gate or a y gate. If my magnetic field is along the x axis, I can do Rabi flopping. So originally, if my state is get 0 and apply a field along the x axis, my Hamiltonian becomes h bar omega sx x over 2. And then my state get 0 evolves. I think it just starts recessing in this big circle. Evolves as 0 cosine omega t over 2 0 plus sine omega t over 2 get 1. So it starts being Rabi flopping. So these x gates, y gates, and z gates are really implemented by the magnetic field pointing in certain directions. And in spin-based quantum information processing, you just have to control the direction and the amplitude of these magnetic fields. Because the frequencies at which the Rabi flopping or the precession occurs omega depends upon the magnetic field. And you so apply pulses, so you change omega or you change time, how strong a magnetic field you apply, in what direction, and for how long, that changes your frequency. That changes what kind of rotation you're applying in single qubit. So, in effect, and this happens in spin based on computing as well. In effect, you have a pulse sequence. So, this is my magnetic field along the z direction. This is my magnetic field along the x direction, for example. So, the magnetic field along the z direction can be switched on and off for some time, t1. The field along the x-axis can be switched on and off for some time, some amplitude. So you get pulse sequences. So you supply pulse sequences to your spins, and they kind of show the rotation on the block scale. And if overall the Hamiltonian has interactions as well, so you have a Hamiltonian, say h bar omega sx plus, say, just to give an example, some constant j s1z s2z plus h bar omega 2. This is the first spin and the second spin. So this is your Hamiltonian. To start off by writing the Hamiltonian for your spin system. So you have the first spin, two nuclei, two electrons, two NV centers close together, interacting to some interaction term. So you have the first spin sees a magnetic field omega 1, the second spin sees a magnetic field of omega 2, and this interaction to write down the initial quantum state and see how the system evolves in time. So you can do 1 qubit gates and 2 qubit gates. They're very convenient in this scheme. And then how do you do readout? So there have to be 4 to 5 criteria for quantum information processing. You need to initialize your states. You should be able to do quantum gates. in a universal fashion. You should be able to read out, you should mitigate against decoherence, which means that your gate should be fast enough. And system should be scalable. There are 5 Vincenzo criteria for any quantum information processing task to become useful. So, your states can be created with spins by the application of magnetic fields. You have these interactions for 2-qubit gates, the interactions for the 1-qubit gates. You also need to do some kind of readout. So how can you read out these spins? So one way to read out the spins is to recognize that these are tiny magnets. So if somehow you can detect magnetic fields, you can read out spins. And this is how they do this in spin-based scheme, purely spin-based scheme, they use magnetic spin. So just to give you an example, if I have a spin that is precessing in the equatorial plane. So if I were to have a coil placed along the y-axis, and this spin is precessing with the frequency omega. Now, since the spin is a precessing magnet, the flux that this precessing magnet creates through this coil is peaking with time. So now you have this fixed coil and you have magnetic spin magnet precessing at some frequency omega. The flux through this coil, which is the magnetic field times the area of this coil, is changing with time. It is changing at a frequency omega. So now if I put a voltmeter up here, so this is a classical measuring device that you need for this kind of quantum. You put a voltmeter here, that will produce a voltage to do the change in flux. Faraday's law. And if you plot that voltage with time, if there is no decoherence, this is what the voltage is going to look like. Okay, and the frequency of this voltage is going to be omega. In reality, your voltage is going to decay with time due to decoherence. Okay, so if you take this time dependent voltage and plot this in the Fourier space, you will get the peak at a particular frequency, F0, which is the omega over 2 pi, which is the precession frequency. So you get spectrums from the system at different frequencies. Okay, so this is how you do readout for these nuclear spins or electronic spins. The problem with spin, however, is that the signals that you get are generally very, very small. If you just have one spin, electron spin, you know what the magnetization of that spin is? It's just the Bohr magneton. Just the Bohr magneton, which is really, really small, but has a fundamental unit of metrology in magnetism. Just the Bohr magnet. It's very hard to measure. But there have been demonstrations of experiments in which you can measure the spin of a single electron. The detectors now are not the Faraday coil, they are squid-based detectors. So in this paradigm of spin-based quantum computation, it's possible to do readout as well. One implementation of a spin-based scheme is through nuclear magnetic resonance, NMR. Now in NMR, nuclear magnetic resonance, just have a test tube in which you put your liquid, and those liquid has molecules in which there are nuclear spins, which are spin off particles. And then you put all of this inside a magnetic field, strong magnetic field, B0, in the Z direction. And then you have other coils along the x-axis and along the y-axis, which are outside or inside this big coil. So a large Z field is applied, and on top of it, you can apply a pulse sequence in which you turn on the current through this X and Y coil so that you can apply X and Y fields as well. So the nuclear spins inside the sample will reorient according to the pulse sequence, and 1 and 2 qubit gates can then be implemented very easily. The problem is that these nuclear spins have even smaller magnetism signature than electrons, because the mass of electrons is larger, the magnetic signal from electrons is larger, so 670 times more magnetic than a proton electron because of the gyromagnetic ratio. So nuclear spin is very hard to detect, and that's why you cannot need a very large number of these nuclear spins to produce a signal that is strong enough to be detected by the coils. So in this kind of quantum computer, you do not have a single spin, you have an ensemble of spins. And the other problem is that if you increase the Hilbert space, which you have more and more spins, if you look at the Boltzmann distribution of spins inside that manifold, the population difference between the different levels goes down and down and down, exponentially decreases. The signal is even smaller. But this is the general scheme of doing spin-based quantum information processing, very different from photonic implementations, but very easy to understand and implement, especially when you work with NV centers. Because NV centers act as fictitious spin-half particles. I think Ojamai would like to stop here, and now we can have any discussion or anything. I think you can moderate and you can okay if you want.
Ask questions. See if I can.
Hey, can I ask one? In your first presentation, you mentioned about measurement-based studies. I'm just wondering, is it considered completely quantum, or it's just like a hybrid system? It seems to me kind of hybrid. As soon as we have measurements, then the quantum system is gone. It becomes a classical system. So is it a discussion in the science?
Right, so generally if you kind of believe that measurements are classical, then you're right, it's like hybrid system. But even in the quantum computer, your eventual measurements are classical, aren't they?
Yeah.
The eventual measurements are done with classical meters. So your pointer state, which gives you the readout, is a classical process. However, recently in the field, I think in the last 5-10 years, the kind of bias that we have against measurement has gone away. Generally, it was thought that measurement is bad and it gives you the quantum to classical transition. But now the system has altogether changed. I mean, measurements are extremely useful and they are part of the quantum process. So, two areas that I would like you to approach. One is, of course, measurement-based quantum computation. It is you truly doing the computation, which cannot be described classically. You're implementing quantum algorithms through measurements. So I don't think it's fair to say that it's a hybrid system, it's a quantum system, and measurement is being used to an advantage over here. Right? If you look at the one big teleportation scheme, the teleportation trick from Boltzmann and Schwann. So you're doing a measurement on one qubit, but that is immediately determining what the other qubit is going to be. In quantum teleportation, you also do a measurement on 2 qubits in the best state basis. And that immediately determines what your qubit, the third qubit is. You can't say that this is a classical scheme. So measurement can be a part of, it can be put to the advantage. And I don't think it's fair to say it's a hybrid system. Okay. And there are different kinds of measurements, right? There is projective measurements, there are POVMs, positive operator value measures. POVMs are an important integral component of another scheme that I work on with my students that is called quantum weak value measurements. In quantum weak value measurements, you are looking at the expectation value of an operator which is derived from a partial trace of a classical and a quantum system. So in a classical quantum system, you trace out the quantum system, you're left with a classical pointer state. So, and that shows remarkably quantum effects. So it's very hard to kind of dichotomize between quantum and classical. Just a few months ago, a very important book has come out. I would recommend reading that book. That book is called Quantum Measurement. It's written by Sabieh, who is at UC Berkeley, and Jordan, who is also in California. Beautiful. So very good, nice book that describes how quantum measurements are important and what do they really mean, even from a philosophical standpoint.
So, you speak about the photons and initialization process and the process. Are those processes, I think, the photons initialize with multiply and entangle with process and measure the out stage, or you already such as the class. Is this process hard? Yeah, I don't know how it would be hard in the implementation side. Could you give maybe tricky point is an important point for us, maybe beneficial to us, describing the process?
I think photons are easy to create in precise states. Even entangled photons are easy to create. They're easy to measure. And single qubit gates are really no problem as far as the experimentalist is concerned. 2 qubit gates are a problem. So before measurement-based computation, there was this paradigm of using non-linear optics to create and non-linearities to create 2 qubit gates. You can read upon Kerr non-linearities. So Kerr non-linearities was one way in which you could create 2 qubit gate, but the process was extremely and remains extremely efficient. The only problem with the biggest problem with photonic implementations, I think, is of scalability. So it's good you can work with 4 qubits, 5 qubits, 6 photons perhaps. But how do you work with 100 photons at a time? Because the race currently in terms of to quantum precise is being won by leaps and bounds by squid-based implementations or by neutral atoms. So they are now talking hundreds of qubits. How do you get this scheme in photons? You can resort to measurement paradigms such as finite photon sampling. It's very complicated. So I think the problem with photons remains biggest problem of scalability. There's not as big a problem as errors and decoherence as of scalability. How do you increase the size of your system to make anything more useful? And the other thing, which is a technological challenge, which I'm not kind of into that field, but I think there are other professors in Turkey who are really into this field and thinking this is going to be second workshop, a big workshop, real workshop on photonic quantum computing later this year, is about making a device, an integrated device that has everything on a chip, everything on a small substrate. Because right now, the experiments that I showed you, some of the experiments, little experiments, modest experiments that we do, they're in free space, they're on large kind of bulk areas on a table. But if you really want to go into the applications, you have to make things miniaturized and integrate them. So how do you make waveguides for photons and on integrated chip? How do you multiplex different photonic signals going on your chip? Because you want multiple signals to be there. You want high bit rates. So how do you make a chip and integrate all of this? How do you put single photon emitters on a chip? Right now, all the single photon emitters that they are incompatible with chips. For example, they are produced externally to the chip and then they are made into the chip. they are fed into the chip through some mating mechanism. So how do you make single photon emitters on a chip to quantum dots or other schemes? It's slightly unclear at the moment. And then when you have things on a chip, you don't have vacuum or free space any longer. You have refractive index of the waveguide. Each waveguide will have a particular dispersion. That dispersion is how with wavelength the properties of that waveguide will change. When you have dispersion, that's a form of loss and equivalence for photons. Then you would like to have continuous variable quantum computing, in which you not so far in this workshop only looked at discrete systems. But it's possible to use continuous variables like position, like key states, to have these additional uses of things. All of this is challenging. So I think two big challenges remain. One is of integration and the other is of scalability.
I have one more. Uh, you introduced a cluster state with for photon. You said also we can increase the photon size, photon numbers in the cluster. Is it any specific thing for increasing photon, like taking feedback and controlling the circuits for specific application? Is there any thing for increasing photon numbers for the cluster?
So far, what I've shown you is very simple, is that the cluster is fixed. So you start with the cluster and then you progress in time through the cluster. But it's possible, so you want to build a large photonic circuit. The elements that I showed you, the box, the horseshoe, and the linear, they are primitives. Primitives means these are elements which form a universal set. And you can combine them to create bigger multi-qubit array, multi-photon arrangements. Now, so far I've shown only fixed clusters, but in many implementations you will find that these clusters can evolve. Once you have created a cluster, you've done a particular computation, then you have a second cluster already there, a resource available, you can fuse the two clusters and create yet another cluster. So it's possible to do measurements and fuse clusters together, so that the cluster size grows, decreases, grows, or the cluster altogether changes during the course of the computation. So I would recommend you look up fusion-based quantum computing. And there are fusion gates that one can implement on photons. And there's a very nice paper, very nice tutorial by a professor named Sheffield Peter Koch. Now, Peter Koch describes fusion-based quantum computing, which are adaptive clusters. Clusters grow in time, change in time, they change the shape and morphology in time. And you can do this very easily with photons. So, have you ever come across the idea of kind of entanglement swapping? Just to give you an idea, so if you have two entangled pairs of photons, one pair is AB, the other pair is CD. So now, is it possible? Now, A and B are mutually entangled. C and D are mutually entangled. Both of them are APR pairs. Now think about this. If you have a circuit, you here, you do measurement here, you do measurement here, and then you kind of feed in these measurement results to some gate here B and some gate here W. Then it's possible to make qubits A and B entangled. So initially, A and D will, A, B have nothing to do with C and D. But doing, so Bob has two qubits B and C. And we do a measurement on B and C qubits, A and D will become entangled. This process is called entanglement swapping. So this is like we have four qubits, two qubits are entangled, you borrow the cube entanglement and share it with another pair. Entanglement swap. This is like a swap pair for entanglement. So this is one simple example of fusion. I think you should come up with a circuit that achieves this. It's an example of fusion. So it's very easy to do fusion-based quantum computing with cluster states. You have clusters that merge into one another. Two clusters combine and coalesce to form a bigger cluster. Through measurements. So through measurements, you can fuse clusters, or you can change the shape of clusters. I think this is a really important and very exciting area. And these are actually areas which are not yet fully explored. I recommend reading Peter Cox tutorial on fusion-based quantum computing. This is the key. I think this is it. Otherwise, you can't find it and share it. So, how Turkey is, I think, really leading the way in quantum hardware and quantum ideas. So, I hope there will be more excitement in the years to come. And I think there's new roadmap is also coming. Yes.
Measurement-based quantum computing is about number of qubits. Then for a qubit we apply a matrix X apply then do measurement. For the others we do the same, right? So we have two axes and three different rotations. And in the end we get an arbitrary rotation about an arbitrary axis. So my question is, if we can apply a fixed axis rotation to some qubit, why we do not apply directly three operations to a qubit, and why go through all these stages of measurement? So we can start with a qubit and apply a rotation and another rotation and another rotation. Why is this not possible, or is it possible?
So the original motivation for this idea of measurement-based quantum computing is sometimes it becomes, for some schemes, it will be very hard to apply unity gates. So the advantage and the promise of cluster computing, cluster state computing is that really you don't have to apply any unity gates. If you have the initial resource available, which is prepared offline, the entangled photons or an entangled state, or the cluster state, which is called the cluster state. Once you have the preparation of the state, no reversible gate is ever applied. You don't apply any unitary gate in this quantum computation. So it might be very hard to apply unitary gates. Or the unitary gates that you apply in certain implementation are so slow that the decoherence kicks in. So, in fact, memory-based computation is so promising because you don't have to apply any gates yourself. Measurements are easy to do, right? So that was the promise.
Yeah, but for example, we apply Z alpha or Z minus.
Z alpha, that's not a gate, that is just, it's like, what basis are you measuring? It's easy to do that in some implementations.
But isn't
A Z alpha is measurement in some basis.
but in formal way, isn't the gate as well? But
Right, and you only, by the way, you only apply Z gates. So there is no need for an X gate or a Y gate.
Z gate combined with other one.
Combined with the header mod, yes. That's it, that's the only set you need. A Z gate with the header mod is not a universal set. You have access to some simple gates. You can also do all computation with just X and Z gates, X and H gates, sorry. So sometimes it's easier to do one kind of gate as well. So for example, in the spin-based quantum computation, what does measurement along a basis of different alpha mean? It really means that you change the orientation of your body. So it's easy to do this in some. Suppose you have only beam switches. Just with beam switches. And initial half wave, perhaps. You can do all kind of unitary gates. So the requirements are less strict. Only thing is you need to create the resource. Everything is in the resource that you initially create. You have a question?
Actually, let's say we want to make it like we want to run a quantum by using like cluster state approach. We have a like fixed cluster state like graph actually. So does the measure direction matter? Like can we like start with by measuring the like
Other end.
quantum photons?
Not will result in a different gate. It will result in a different computation.
Yeah.
So the order is important. That's why when I kind of describe all of this, I kind of label the qubit 1, 2, 3, 4 in a particular fashion and measure two earlier than the other. That's why it is one way. One way means that the order is important. So it does matter. So a unitary quantum computer can be done either way. You can make the end the beginning and the beginning the end. Still works. You will do the inverse operation. But here the order is important. That's why this is one way computing. So the manner in which you draw the clusters. So this horseshoe cluster is different from this horseshoe cluster.
Yeah, cluster is of course
Preparation wise, it might be identical. But the order and sequence of measurement is going to change the computation. That's why it's one way. By the way, one important aspect of one-way computation, if you're interested in looking for research problems, if I had the time, I will want to do this, is one-way quantum computing from the perspective of thermodynamics. So, remember that if you have a quantum computer which is reversible, the entropy of the system through unitary gates is conserved until and unless you make a measurement. So the information, so if at each stage you find out official information between two sub-parties, it's you have bounds on that because of the unitarity of the process. But how does one-way computing look like from thermodynamical perspective? How does the entropy of the system change as you go on? How does it satisfy the second law of thermodynamics? The entropy of the system is constantly going up. And how is the entropy progressing as the measurement progresses? So what's the best kind of cluster state that can be made? What's the best resource, minimal resource that can be made to do a certain task? So these are problems in thermodynamics. So these are very important.
Consider the entire system, although you are applying a measurement and collapsing the degrees of frequency so to a certain subspace. But if you look at the entire system, including the auxiliary qubits, isn't the entire system is a unitary evolution?
Right. Because once you have information from the measurement outcome, the energy is information is, and isn't the entropy lost? Isn't the entropy gone up?
I mean, in the measurement side,
Mhm.
you are collapsing it to a certain subspace. So, there is a loss, increase in the entropy.
Mhm.
But if you consider the auxiliary qubit also, the entire thing is, shouldn't it be a unitary evolution? The entire,
But
if
from the
it
system,
is unitary, then entropy also, remains the same.
of course, the entire universe for the entire universal system, plus the surrounding and the measurement, it's of course entropic. But now information is constantly lost, it's being measured, information is gained in fact in the process. So from a systems perspective, the entropy keeps on changing. So that is what I meant to say. The entropy is changing. So if you want to do particular quantum computation with measurement based schemes, how big a cluster size do you need? So this question can be answered from a thermodynamical perspective. So how much entropy loss in the system can you afford so that the second law of thermodynamics remains valid and you get your entire you get your intended computation achieved as well. From that perspective, how much resources are needed? I think that's what I want you to think of. How big a cluster size do you need to do Shor's algorithm with 5 qubits? This is one example question. I want to do Shor's algorithm 7 qubit, I want to factorize number 15. How big is cluster size do I need? What's the minimum do I need?
Can we go to point out about that, or would you have to? Can point out, is there a stage point out?
I think that's the open question at the moment. How do you find out the resources that are needed? So if you prepare a cluster state, even if you were to prepare a cluster state, what is the minimal degree of entanglement that you need? These are open questions, I think. No one has touched and or very few ideas in that direction exist. So this is my thought about this. But these are open questions at least. Any more questions? If you ever visit Pakistan, you're most welcome to come to our laboratories.
Okay, so thank you for participating and thank you, Professor, for this very exciting, series of lectures that was enlightening to all of us, and we hope to pursue further collaborations in these areas, inshallah, in the future. Thank you.
Thank you very much. I'd really like to thank you, both of you, for letting me. You can send the PDFs to
Yes.